So I'm going to go ahead and get started. I kind of taught this lesson when I was doing a lot of work with National Grid. It's very important in the electrical industry to bring up safety. We are dealing with very high power, and it's not something you want to mess around with. You want to understand the issues about electrical shock. I've seen some horrific things happen to people that have not basically followed the issues of danger and voltage and power, because it is an invisible source. You can't see it until you touch it. So make sure you take that into consideration. My name is Roger Fritz. I appreciate everyone joining today. I'm very thankful to my father. He started in 1953, actually installing wind chargers in Nebraska. The old DC where they put it to the battery, that's how they got their radio. I'm second generation. You see on the far right, that's my third generation or fourth generation grandson. My sons are in between there. I have a couple sons in the business, and then seven grandchildren now. I'm very fortunate, blessed. So over the last, let's see, my timeline says 37 years, now it's been over 40. I've worked very closely with the utility companies, PG&E, Southern California Edison, National Grid, Eversource, many of the power companies, to implement energy efficiency programs, with variable speed drives and determine where the actual opportunities of savings are. My father also started an electric motor company in 1955. He had, started rewinding motors. And then, went on to manufacturing many different types of equipment. My brother does run the 7 companies in the Midwest that are all under the motor industry. I have a son that's runs the drive control industry, 508 UL shop in the Midwest. I also have another son on the East Coast who does a lot of drive controls for the power companies yet. Let's see, I get my contact information here. If you have any questions, you can send it to engineering at AC-DC-HOTLINE. There's my phone number to help understand rotating machines. I am 64 now, so I'm a little bit semi-retired. I still do a lot of work. I don't know if I ever will ever totally retire. But I feel it's very important that we pass on information that can help our industry. I've got a lot of friends in the industry all over the world. Currently I have about 30,000 LinkedIn members, and most of those are electric motor people. Barnaby was going to join me today, but he got called off site to do a couple of urgent, breakdown issues on some big DC machinery. Barnaby is a partner of mine that's in England. He does a tremendous amount of specialized controls, drives, soft starters, you name it. A brilliant guy, and he will be on other and future discussions that we have as we go forward. I'd also like to give you the opportunity to join. This is being produced today by the Nikola Tesla's today's Solutions and Collaborations group. There's 2,500 of us approximately in that group. You're welcome to join it. Just put in Tesla's, I think it's Nikola Tesla's Collaborations. It'll show up, and you're welcome to, request to join. I feel he wrote the Bible on electric motors and machines, alternating currents, and has been extreme influence in my life. And I've done a lot of research and study to his information, and I do see that a lot of the technology he developed well over 100 years ago are now coming back forward. So
when you think of electricity, you think of Edison. But there is one electrical genius who is nearly forgotten. A man who dreamed of giving the world an unlimited supply of energy. His name was Nikola Tesla. This is the story of a modern Prometheus who changed the world with electricity. It was Nikola Tesla who captured the power of Niagara Falls with his alternating current system and made it possible to transmit electricity to all of America and the world. Suddenly knew he could recreate this rotating field by powering the coils of a motor in different steps or phases, like the pistons of an engine. The resulting forces of magnetic attraction and repulsion would literally twist the rotor in a circle, the electrical equivalent of the wheel. And all this was accomplished with alternating currents. It would soon turn the wheels of industry around the world. Tesla was ready to unveil his motor to the world.
The subject which I now have the pleasure of bringing to your notice is a novel motor which I am confident will at once establish the superior.
So what I like to do is bring it back to the very basics of what we're really doing and what we're really operating. And because I've been a motor winder since I was 10, my father started me winding coils for motors and helping insert them when I was a little bit older, and then understanding, electrical connections inside the motors. And what we're basically doing is we have typically, like this shows a 4-pole stator. That's only one phase. So a 3-phase will have actually, 3 sets of these operating inside the motor. But what we're doing is we're inducing power in these coils, creating a north and south magnetic poles in the motor. And on the rotor, we're inducing the induction into the stator. And so then what happens is it actually creates a repelling one inside the motor. And so by having sine wave power, which is what we get off the generators, so the real difference between a motor and a generator is we have a excited rotor that's turning inside this, and it actually induces the power reverse and turns it into a generator. So the motors, have this, rotating field in here, and it's all based off of the sine wave. Well, the issue is that in the United States, they give us 60 cycle power, meaning that they're turning these 4-pole machines at the generation site at 1800 RPM, and that produces the 60 cycles per second of our AC power that we're used to seeing every day. Then they use transformers to step up and down the voltage throughout the range. So the beginning of it typically is that when they had the power to the motor, creating the sine wave is here, which is like the voltage or input source. You have line 1, 2, and 3, which is your 3-phase power. And I'm not going to go into single phase, as we could do that another day. It's a little bit more complex, but what we're doing is still creating a rotating field. So you have phase 1, 2, 3. They have just a set of contacts here as the old starters, and you turn that on, and then this is the overload. They're like thermal coils that sense how much current's going through there. And what that does is if you're doing too much current to the motor, it'll actually cause failure. So what they do is they have these sensors in here, and then it simply opens up a set of contacts here that are in the start circuit. But originally we just basically turned it on. Well, when you turn it on this way, because the motor is not already creating what they call counter EMF or voltage back, the motor will draw, depending on its resistance and inductance of the motor, it will draw between 3 to 6 times its nameplate. So if it's a 100 amp nameplate, it'll draw 300 to 600 amps very briefly just to start it up. And that's what the power companies are wanting to get away from, is so that they soft start. So from this, the secondary way they were doing it in soft start, and almost all motors in Europe were done with what they call the Y delta. This is also another way of doing it, where they they split up the winding and they do it what they call part winding. So what happens is half of the winding is shut off, and it allows the motor to get rotating up to speed. So normally a part winding start will save in inrush current, it will cut it in half. So instead of that 600 amps starting, it'll draw 300 amps just for a period of time till the rotating field gets up to speed. Then with contactors, it brings in the secondary winding set of windings. This is the way a lot of it was done in Europe, and you'll see the IEC nomenclature. These are the numbered lead numbers, and a lot of them you'll have like a 12 lead motor. Well, they were doing this again to stop the power. So they call this Y delta start. You can either do it on 400 volt system, 480, or 230 volt systems. But literally what was happening, it was taking this circuit, and this is like one set of the phases. If it was on the high voltage side, you'd tie 4 and 7 together. So this would give this motor light, when it was actually operating, to be running at 480 volts here. Well, if you tie 10, 11, and 12 together, it creates it into what they call a Y configuration. And what happens then is the actual voltage across this winding ended up being roughly 1.73 times the amount. So the voltage would you could provide 480 to the top of the Y, and it would end up giving this part of the winding, it would give about 277 volts. The benefit to that was, again, it would drop the inrush current, cut it back, typically in half at least. And that's what this contactor over here is for, that does the Y, or the star they call it. And then after it gets running, it's got it across in the delta. So KM2 and KM3 will pull in, and that'll end up, giving the motor back again full 480 to that winding. So all we were doing is basically just reduce voltage. They also had auto transformer starters, all kinds of things out there to eliminate that inrush. The issue is that some applications, if you did the part winding start type starter, what would happen is the motor sometimes wouldn't have enough torque. So if you had a fairly high torque application, it would really reduce the torque and not produce enough. Where a Y delta, you still had all the windings engaged, and then after a period of time, it would trip on over, give it full power. That you would get a lot more torque. So that tended to be a little bit more of a standard. It was easier, it had more leads coming out of the motor, which are basically connections on the individual windings. Then was came out within the, I'd say the 70s, the soft starter, which was basically, these are thyristors, meaning that you had your L1, L2, and L3, and it would, this is just a disconnect switch, it would be between it and the motor. So this is a little bit more detailed, drawing of it, but what was happening is these 3 sets of thyristors were in series with the motor, and when you bring your contactor on, and what you're able to do is you're actually able to fire how far on the sine wave is. So again, back to our original sine wave power that we were creating back at the generator. So here we go. What was happening is, here was our sine wave that we were getting the AC voltage from the power source, and we could tell this device in both the positive direction, meaning here going positive, or negative. We could tell it when we wanted how much of the waveform to actually get to the motor. did soft starting. A tremendously helpful device. Saves a lot of, a lot of the inrush startup current. In certain areas, doesn't make a big difference in your demand charges. I feel this technology is very good. I think it's very controllable today, and it really, can do a lot of things, and we'll go into that a little bit further. Then what came about is the VFD technology. I was trained in this in the 80s very heavily. And what it's doing is basically have phase 1, phase 2, phase 3. You got your sine phase power here. It goes through diodes, and the first thing we're doing is we're back building DC, which is what a lot of the original variable speed was DC power, because you could vary the voltage and it would actually vary the actual. A DC motor doesn't have this in it. The DC goes directly on, to the motor, but the motor has to be a DC motor with either permanent magnets, or it's got to have, commentators in it, which basically allow it to shift the phases to get it to turn. But the bottom line is so the VFD came on, and they had these bridge diodes on the front end. This is what they call a link choke inside the drive. Some people will put coils out here, and that'll be what they call line reactor, and that will dampen it. I'll get into the reason why they did that. Then it has capacitors in here. The issue about the capacitors is these capacitors, if you look at all the manuals of the various drives, they have about a 10 to 15 year life, depending on the design, because they get hot, cold, hot, cold, hot, cold, they dry out. And then after a period of time, they actually want to short out. So we haven't got, that totally solved yet. They went to oil filled, but they have to be, so much larger. But this is a weak component here, inside of a VFD, is those capacitors after about 10 or 15 years old. So they do need to be checked, towards the end of their life. Then these are transistors, and they've had various types of transistors out there. Used to be GTRs, which were gated transistors, meaning that the gate voltage that turned them on and off was the same as what it was switching. Then they went to IGBTs, which are isolated gate transistors. And so what it does is, you can see on the far right there, it shows we're giving what they call PWM, pulse width modulation. So the first ones were 6-step. We didn't have the microprocessors that could fire them and control them as well. So we were doing this like 6 pulses, and it was very jagged. It ended up creating a lot of noise in the motor. You could hear it. And then they went to, like I said, the isolated gate. We're able to get the firing circuit up. And a lot of them were roughly about 1,000 to maybe 2,000, what they call kilohertz. That's your carrier frequency of this pulse width in here, and how fast that pulses. Nowadays, you can buy them as high as a better VFD is in the 12 to 15,000 kilohertz range. But all that has to do with the more you fire it, excuse me, the more you fire those transistors, the larger they got to be, and the more heat that they'll produce. So they tend to try to want to keep the carrier frequency down, but creates more noise, and on the backside, it's a little bit more detrimental to the motor. So again, this is more of a look at the red is the actual current flow that's feeding out to the motor. So if you look down on the oscilloscope, you could actually see that this is more the sine wave. And what we're doing is we're controlling what we call the frequency here. So the faster or the slower, or the sooner we switch it from AC to DC, we can speed up the carrier frequency, or we can slow it down. So on some applications, if you have a pump or a motor that you're not quite producing enough, you can actually bring the frequency up from what its base frequency design was at, 60 hertz, you could bring it up to 61, 62, 63 hertz, and it'll actually speed it up and it'll make the motor run faster. So the 4-pole machine will run, instead of 1800 RPM base speed, it'll actually run all the way up to 2000, 2200. The mechanical characteristics you have to really look at, on your pumps and motors, but it is a way to get a situation where if things aren't quite balanced enough, you can bring them back into balance. So the thing that I want to talk about is that when you're back here and you're pulsing this power, feeding it into the motor, you also create what they call extra harmonics. And so this is 3 times 60, 5 times 60, 7 times 60 hertz. You get, if you look at with an oscilloscope, you'll get these ripples, and it's called harmonics. And from that, what'll happen is you're doing what they do with radio. So you hear like 800 hertz or 1000 hertz or whatever. That is harmonics, and that's how they create a radio. So they send a transmission over these frequencies. So this has caused some issues and concerns with the power companies, because noisy power ends up chewing up more power. So this shows like the harmonic order that you typically see on a 3-phase. You have your fundamental, power at 1, and then you have it at 3 or 300 hertz, or 3 times 60, 5 times 60, 7 times 60. And typically the 5th harmonic is one of the higher ones that you have to be cautious of. So what I'm talking about is that, so you have your sine wave, which is your AC power here, and you've got these, this shows the current waveform, and this will vary, the current waveform will vary based off of where the load is and when those capacitors back here, when these capacitors need to recharge and keep that DC to the right amount. So these will trigger and fire off of that sine wave, which is the actual AC power. You'll see the current flow that comes out of them is nonlinear, and so it's called nonlinear loads. What happens is that when you get this irregular harmonics and noise, if you look at an oscilloscope, you'll actually see the input voltage actually start chattering and having noise. It also is very critical that you look at the wire and the insulation coming in to the VFD control, because if this ends up getting too high over a period of time, so a lot of them have gone to shielded cable, they've gone to various ways to basically ground and get rid of that noise. And I'll go into what they call harmonic filters here fairly soon. So again, you get these extra jags, and this is what we're worried about, is keeping that original generated power that was out there controlled so that we do not create other issues. I've seen I've done a lot of plastic machines. I've seen this 3rd, 5th, 7th harmonic actually create pulses and noise, and actually radio noise. It'll actually affect the color feeders into motors, into the molding machines. It'll change telemetry. It'll damage other electronic devices. So power quality is important. And this phenomena happens also in DC machines, because we're also creating DC the same way back here to create DC, but we break this part of it off and we actually go out and feed to a DC motor. So what a VFD is doing is we're basically, again, controlling that frequency, and we're controlling the voltage amplitude, and we're doing that with PWM. So this shows if we're doing 10 hertz or 10 cycles per second, how much further apart we have to, create the PWM. Then if we bring it up to 20, and this is all regulated by your processors, it goes on up here, and it actually, again, gets a little closer, 30 hertz, and then, all the way up to 60. But if you look at it on an oscilloscope, you're going to see this kind of an actual feed. You're going to see all these pulses, and it creates a lot of noise. I'll say a little bit. So what I really recommend, and I found this metering to be extremely good, and if you are very heavily involved, I highly recommend you look closely into this meter, and I'll let it tell you a little bit more about what it can do. You're measuring those 3 phases in, and it's also got voltage probes that go across the power source and allow it to actually read with scoping what's going on.
Introducing the Fluke 438 Power Quality and Motor Analyzer. The Fluke 438 is a multi-purpose test tool designed to improve troubleshooting on electric motors and minimize downtime. Whether you're in a process plant or discrete manufacturing, electric motors are critical to your operation's success. The Fluke 438 lets you quickly gauge electrical performance, power quality, and mechanical performance of industrial motors. Using 3-phase electrical measurements on the input and motor rating plate data, the 438 calculates torque, the most critical mechanical performance variable, speed, load on the motor shaft, and overall efficiency, without the need to install mechanical sensors. All this with a single tool, and all while the motor is running so you don't sacrifice uptime. Power quality issues, such as unbalance and harmonics, can cause motors to run hot, eventually stressing windings and accelerating failures. Motor failures lead to costly downtime, and the cost of waste associated with inefficient motors adds up. When testing direct online motors with the new Fluke 438, you get both power quality information and mechanical performance data in the same test with a single tool. With an intuitive user interface, optimized current probes, and at-a-glance motor status screens, the Fluke 438 gives you the motor troubleshooting information you need to make better maintenance decisions and keep your plant up and running. Contact your local Fluke representative to learn more.
So the reason I talk about that is I've used that meter now for well over 20 years. It's advanced quite dramatically from when I first started playing with it. But again, this shows that voltage waveform, and then it also it shows from those probes, it shows the current waveform. So you actually see what's really feeding out to the motor, because a lot of people are used to just putting on a clamp on amp meter, and it's just digitally telling me these values, but it's giving you what they call the RMS value. So it's not what the actual spikes are, it's actually what it actually is calculating. So you may see it's showing 20 amps, but you may not see that the actual, there's maybe a large jag or spike in there. And that's what motors don't like. Windings of motors are very critical. So back to the VFD technology, there's a lot of, power companies are requiring that you put various types of filters on the motors. And there's everything from, DVD filters, there's just a straight line reactor. And basically what it is inductors and capacitors. So I like to get it back to simplicity. Back to the original point in time is when we had the original power just feeding from the power source. We were feeding that motor directly. It was getting clean sine wave power. You had less failure. The motors tended to be more robustly built, back in the early days. I was back around when the U-frames were around, which were the motors for 1 horsepower is like twice the physical size what it is today. a lot of people want to push high efficiency, high efficiency. It's real important that we actually look at the efficiency of the system, not so much the efficiency of the motor. The motor, between a standard efficiency and a premium efficient, may only be 3 to 5% difference in actual, power use. So that isn't where the efficiency typically comes from. Again, the meter can show you back here some of the peaking power, spikes, jags. So you can actually get it down to a point of, what did cause that power. It's connectable to either a Y source or a delta source. And it's important that you, when you do set them up, you set that up. And that means, what is the transformer providing for power, into the unit. It has a tremendous amount of logging capability over time. So it has a logger built into it, got a menu, it's got a scoping functions. It's got a setup where you set up the values, you set up your Y, delta, your ABC phase. And then I'll do recording over days, weeks, time. So I highly recommend it. But back to the requirements of noise and filtering. So not only do you get harmonic noises from that pulsing on the input, so you have to put a lot of times that link choke that I talked about earlier, or the line reactor, but you've got to put something in front to basically slow that semiconductor diode from just instant, because when it gets power, it instantly shoves it into the capacitor. So it's important that you also, a coil in the circuit resist change, a capacitor accelerates change. So that's why you used to see, for power factor correction, they would put, capacitors on the front side, and it would help balance the power factor out to the motor, and we'll end up, drawing less, true RMS amperage that you would see on an amp meter. True kilowatts was all based out of how much torque are we getting out of the rotor and power. So then they've gotten to where they had the harmonic filter on the front, harmonic filter on the back, and you add additional losses in the circuit when you do that, because you've got resistance and load in between it and the power source. And so the actual power produced, to the motor drops. So some of these will be 3% inductance on the front, put 3 to 5% inductance on the back, plus you got the VFD losses, plus you've got the line reactor and the capacitor losses. So, pretty soon, you got to be really careful of what is the power source. So this is like a before reading, before they put the filter on. You can see, again, there's the voltage. You can see the jags from the PWM, and you can see what it was doing, actually to the voltage. Then when they put the solutions of these inductors and capacitors in there as a combo, what will happen is the actual waveforms will clean themselves up. And this is what the power company likes. This is what it is. It also makes it more efficient on the input and more efficient on the output. But it does cost money. It is expensive, to put these on. So a lot of times, people are not necessarily using them, even though I believe they should. So that kind of discusses, again, I want to do a little recap here, that the original, it's called the old man's way of doing it. We basically just had a starter, turn it on. The power company had plenty of power. We didn't really care. So, 5 to 6 times, the inrush, motors got up to speed. They were on clean power. They ran smoothly and, had less failure. Then they went, part winding start, which was also done back then. Then it went to, where you put in half the winding and then the other half the winding. Then you also had the Y delta starters, where you basically connected. So you had 277 volts here first. And then when it was connected back to the the line again. So it connected it out into a Y format out here, and then brought it back. And then you had, again, lowered the voltage to the winding as we started it, and it would end up basically cutting the inrush in about half. Then we had the soft starters, which were the thyristors, which we were basically turning on and off, controlling, and we're basically controlling how much voltage gets to that motor, so we could really, keep the currents down. So soft starters today, I think, are a pretty prime choice of what should be done if you take into consideration also a lot of the mechanics that are required. So this is again what the soft starter was doing. It was taking the sine wave when we turned it on, when we turned it off, to the power source, and it would tend to, then we went to the VFD, which is a more complex, where we had a diode bridge front end, capacitors, inductors, transistors here, creating PWM out to the motors. Some downfalls are the harmonic issue that got to be taken care of. So back to motors again. I highly recommend this group called ESA. They're out of St. Louis, Missouri. It's a worldwide organization, and they have this little pocket electrical engineering handbook. I think it's like my little Bible, and it allows you to actually understand what's truly happening to the motor. ESA is a group of motor rebuilding people that got together in 1944. My father used to be a chapter president and director of this organization. From that, they developed this little book. It's got frame sizes, amperages, nominal efficiencies, wire charts, and I just highly recommend to look at it, because the factors that people lose track of is when the voltage changes. Again, what the generator is really designed for, let's say it's 480 volts, the motor was designed for 480 volts. If the power getting to the motor isn't 480 volts, the motor, for what it's designed, it feels starved. So as soon as the voltage drops, you still got the torque going out the shaft. So what happens is the current rises. Well, the motor winding had a certain resistance from the power, and that's where the heat comes from. So you've got to really be careful of under voltage and over voltage. So this shows you in this book basically the effects of both unbalanced, if all three phases aren't balanced, plus if low voltage and high voltage. And a lot of people don't realize that if you look at the factor, it shows here, if you have a 5% voltage imbalance, you're supposed to be derating that motor to 75%. So a lot of people will just look at the nameplate, well, it's a 1.15 service factor, I'm fine, I can run that up in there. But we're basically putting everything at a stress point, which is a design nightmare. And you got the issue about imbalances, beginning ABC, which cause the issue, and they really, drawing too much current, so we get a cooling problem going on in the motor winding. So again, we're going to go back to this, back to the metering, the input, the true RMS power being able to be read. Then they also have these, what they call hobo meters, that are, basically currents you can record over time. There's also a flyer that's available. It's a trifold flyer that a motor tells a story. And so if it fails, you can typically tell what happens. So inside this flyer, it shows you the situation that happens. Like here, this ended up being a surge, because so that surge from those coil connections out there fed into the motor with a high image. Well, this is inductance, so it wants to resist it. So it tries to hold it, and that surge then raises that instantaneous voltage, and it actually shorts the coil out. So that is normally you'll see, from some of the spiking that goes on. This one is actually showing um, uh, phase loss. So this is when the motor was single phased. So this motor, it shows this is one section of the windings. Again, this is a 4-pole machine. Got 1, 2, 3, and 4. You can actually see that because only 2 phases of that original starter were still feeding the motor, the motor failed because it was trying to pull all the load on these 2 phases. This had to be a delta connection in order to do that, because if it's a Y connection, you'll get more of just one load, directly overloaded, because it only pulls through ports. I can just go into more detail there. This actually shows like an over voltage situation between line to ground, or sometimes this can be mechanical rub. The bearings have failed, and so it's turning in there, and the rotor and the stator are not as close together anymore, or far apart. So what happens is it ends up scrubbing, and it burns this insulation paper inside. This one showed, again, a higher voltage that ended up shorting to ground. And then this one shows a higher voltage between phase to phase, and it actually shorted the winding together. So then the motor fails. It has more detail. You can go online to ESA. You can look them up online. You can easily get access to that. What I want to get into now is, which is what we're kind of talking about. My subject today was pumps, and it's very important that we look at pumps. So again, in this little book, it's got the calculation of horsepower, GPM, pump efficiency, but you can also reverse and actually calculate the pump efficiency. So you can look at the horsepower, how many GPM it's going through, and actually, get to the point where we can do, a pump efficiency, evaluation. So when you're looking at a pump, and this happens to be a pump curve, and it's got the brake horsepower. Every motor or every pump has a optimal efficiency point, meaning at a certain speed, certain power, that's where it's the best efficiency. If you're too far on the curve, you're too far back on the curve, the efficiency drops. And it's all based off of the impeller size and the rotating speed of that, and the lift or the amount of pressure that you're bringing back. So you have a certain amount of head pressure that is being fed back. And again, this is best efficiency point. So that's the optimal point of all of the factors that are operating. And so when you're starting and stopping a motor, and get important when you're buying and putting equipment in, it's important that we talk to the pump people about where is best efficiency point, period. So we know. The issue you also have to look at is there's different design types of pumps, but we want to find out from them what's the best speed, what's the best point, and then design everything to that point. So if you're running it at an 1800 RPM, or you're running it at 3600 RPM, depending on the impeller size, where is that good point? There's also satisfactory ranges of where it's best to actually run that, because as you can see, there's certain points you got to be working about is suction, low flow temperature increases, reverse mechanical seals, radial thrust direction, all those mechanical issues are happening inside, the amount of lift and pressure. So when you put various types of starting and controlling technologies, onto a given, motor, you want to be careful where we're at. So this is a software that if you send me an email, I'll send you a link to a guy at the he's got a pumping efficiency group out of Australia that has actually created this very unique software. It basically has where you can put in various speed characteristics. You put in the original pump curve so that you can actually determine, are we staying at that peak performance point? Because if we're not, what I've seen many VFDs, when you're slowing the frequency down, when we're slowing these frequency down, we have to be careful what that effect on the speed and characteristic point of where we are on the pump curve. And you can see it drops off quite dramatically, but also when you change the speed, it actually, once you put these values, it also changes the pump curve. So the curve is not the same because all of a sudden we're running at, 55 Hertz, which is, maybe 1700 RPM. That curve test point that they had at the factory changed. And so it's important that those curves, as they move, they come back and forth if you're using VFDs, because, the formula for, well, the point I was talking about is again, keeping it that best efficient point. But I've seen this best efficiency point by putting a VFD on, you run it down to 16 RPM. All of a sudden, the best efficient point is way over here, and you're not in the optimal, running position. So it's really important that we keep, the motor at this again, and it picks out your best efficiency point, speed and point curve. The differential here can be 20, 30, even 40% plus cavitation in the pump. The pump does not like to run too fast, it loads too heavy, or it doesn't like to run too low because then it loses its mechanical advantage of lifting that water, and it ends up causing a lot of noise. So the thing that was a fallacy with the VFD world is, everybody used, quote, the affinity law, well, which is basically a cube factor of the horsepower requirement based off of speed. But the big factor that you have to look at is what amount of gallonage do I want to produce? So if I want to produce 1,000 gallons a minute, and I want to do that for a certain period of time, and it creates a certain acre feet of water produced in irrigation, at 1800 RPM, yes, it may be pulling more power for that period of time, but it's getting the work done faster. So the issues of these added losses that are out there, in the VFD control world, have to be considered. Plus, the longevity of, how long is that thing going to last? I mean, I've seen, guys that put wells in, in Nebraska in the early 50s and 60s, and some of them are still pumping. And so there's a big consideration. I don't think VFDs are bad. I think the issue is they have to be calculated of all the things that they're actually doing and look at the actual pump curve. Let's see. The other factor that then again, this is actually Dennis Brimmel. He was with the VMR until I actually sad to say lost him about a year ago. He had 50 years experience in vertical turbine technology. And what I see on a lot of pumps, they all talk about the new VFD type motors, because again, that static noise, all information, it's kind of like about 100 horsepower and up. You see it more often than you do in smaller motors. But they actually went to where they insulated the mechanical bearings. They also put this brush ring or grounding rings you'll hear talk about in different motors that basically take off that static. Let's look at it. this static peaking power, and again, that is coming off of a VFD. So that's why they're worried about that peaking voltage, because the insulation may have been designed for 1200 volts, and all of a sudden it's instantaneously sending it 15, 1600 over a period of time. It deteriorates the actual insulation in the motor and the wires going down the well. And the longer that lead length is, the higher the values will be. So what my belief is that I think a lot of pumping applications should be designed with soft starting technology, meaning that we can just trim off the waveform. They're also typically about half the price of a VFD. Accomplishes that soft starting issue so that you don't, overload the power line or do a lot of, voltage downing as the motor comes up. That tends to be, in my opinion, still one of the better technologies. Plus, they're now designed where they can actually, if the motor's lighter loaded, it actually can start, bringing the power again down based off of current, and it can actually lower the current, feeding to the motor. And that was the original Nolan patent that was done by NASA many years ago. That was, basically how the soft starter began. And then the point is doing a good analysis on the pumps and the pumps. If you're going to put a VFD in, look at those curve spots, determine where your proper efficiency loads, and it'll end up saving you a lot of money. And also look at the actual need for total GPM over a period of time that are creating the amount of acre feet of water you need to know. Definitely an irrigation on growth. It's a little different in a process, where we're basically just controlling speed and power to properly maintain a certain pressure. VFDs in a high-rise building in those areas, they tend to be a little bit more advantage. But definitely we got to look at that total harmonic. This is like a VFD modeling software that's also available. I can get that to you for free. You send me an email. I can get you access to this software, which I think is very good, in the marketplace, that can also help. So I've gone for a little over 55 minutes. I'd like to definitely, open it up for questions. I'm gonna check the chats here real quick, see if there's any chat questions. I'm looking right now. So like I said, what I'd like to do is, open it up for questions.
Hello, I'm Dennis Grimmel, Chief Engineer of VMR USA. I would like to introduce you to the engineering features and design philosophy of VMR USA. From field feedback, from new or improved vendor materials, from factory process improvements will and are being implemented. As an example of incremental improvement, we are replacing guide bearing grease lubrication with oil lubrication on our larger frames. This product was limited to NEMA frames from 200 horsepower. Extending the product offering provided BMR with a rare opportunity to design from a clean sheet of paper. I was finally able to build a better design learned from 50 years in the business. The engineering challenge is to implement the best design practices while still providing a cost-effective product. To illustrate this design preface, let's look at basic design characteristics. The output of the motor is directly a function of d squared Lg, where d equals the diameter of the electrical core and Lg the length of the electrical core. So 4 inches in core length can be duplicated with 2 inches in diameter. Actually, the larger diameter performance can be duplicated with a shorter length. Horizontal motor diameters, of course, are limited by defined shaft type. This limitation does not exist for the vertical hollow shaft motor. Increasing the core diameter allows for a short bearing-to-bearing distance, which has significant advantages. The advantages are easier to manufacture, which means inherent higher quality. A superior heat dissipation gives you inherent service factor. It can achieve higher efficiency at lower cost, which gives you a competitive sales price edge. And low vibration signature, inherent for mechanical component life. So we decided to increase the product offering. VMR USA decided rather than increase the length of the 440 frame to the 447 and 449, we increased the diameter and skipped over the 500 frame series to the 580 frame series. To allow interchangeability, we kept the same pump shaft height as the 447 and 449 frame series. Along with several best design features, electrical cores were ventilated to provide the lowest thermal hotspot. This allowed us to provide product offering of 300 to 600 horsepower with Class B temperatures at 115 service factor in 50 degrees C ambient, presuming NEMA normal service conditions. The next increase offering will continue this philosophy. 4 inches in core length can be duplicated.
So I'm not here to promote any one given thing. What I wanted to do is basically give back and give knowledge so that we can get it back, to absolute simplicity. So definitely, if you want to look at it, I did have a one chat question that came up, which basically is talked about is the efficiency, again, of looking at where are you on speed, where are the pump curves, where are we operating the actual motor. And what Dennis was really talking about is building back the motors. Slides. So that we have the old, robust technology. A lot of people have driven so much about individual efficiencies of the motor itself, but they forgot to take into effect that we do need proper cooling, especially in a lot of irrigation where it's in the hottest, places on the planet. We're trying to change deserts back to, irrigated crops. And so we've got a lot of heat factor. So you don't want these motors to get hot. And what he was talking about is the difference between classes of insulation. Early on in the 60s, B insulation was kind of the norm. We didn't have, a lot of the new ceramics and things that we have today. So, then they went to class F, then they went to class H. Well, what they've done then is they've shrunk it all so that the magnetism and creation creates higher heat in those coils, and that doesn't create extended life. So what we really feel the optimal way is to do is to build the bigger, robust, round frame motors and, keep this down to what a B temperature rise is, in those cores and stators. And then that way it can handle that high temperature outside that is out there. See, another question came in. So it's got I got a question coming in. What is the soft starting technology that we recommend when a VFD is not optimal in the drive? Well, we'll go back to the soft starting part. This is where I feel you can, if you talk to the power company and you just simply need 2 starter contacts, you can get by with the soft starting way of part winding. And so basically just bring in this contact. It's the old contactors. There's nothing to wear out other than the contacts over time, but I've seen these things 30 years old and still working. That's the ultimate way. The the next way is, which a lot of the power companies want today, is the soft starting, which are basically, this is the diagram here, which is basically thyristors. And those are basically SCRs that they're on only while you're starting the motor and shutting it off on a normal basis. This is, I feel, the best alternative to a VFD if you have the proper pump curve and you have it all designed. So if you're sitting at the pump at 67, 68% efficiency, you only then have the 2 or 3% loss in the motor. All of a sudden, that's the optimal efficiency, and you're getting maximum GPM, maximum power out. If you need to fix it, you should go in and turn the impeller, and it's producing too much water. Getting again back to that optimal point, back to the pump curves, getting to this best efficiency point. And the pump people run all these tests, and they have the reports, to show us, where they are and, where they should be. A lot of people, I don't know, because we're really strong in one industry or the other, or one, I'd say, piece of the industry, we don't look at the total system efficiency package. That's what's most important, because that's where, when you get running these off the curve, because you're running a little bit too, so they use a VFD to kind of fix their problem, bringing it back in, but they forget about the losses, they're in there. Also got a point is to tell about the question. It says, hi, please tell about the insulation between the coils and coil to coil of a VFD motor. So what the question there is that as we're doing this PWM coming out of the VFD, this is the waveform. You'll see these higher spikes. So this is like peak to peak voltages here. It ends up jumping. And so what happens is, you'll see it on the scope here, these instantaneous little spikes. That winding insulation, the winding insulation was designed for, let's say, 1200 max peak to peak volts. Well, as soon as we get a higher potential between the two, phases of power, and you get this giant spike, those two want to go the least resistance to ground, or to least resistance to create an arc, and it basically just creates a spark between, and then it burns insulation out. So that's what you have to be careful with the VFD, is that the peak to peak output voltage. There are, better drives out there that have, snubbing on the transistors. They're a little more expensive. And then you also have, voltage to ground. If the voltage is getting too high, it wants to go least resistance back to the steel stator, which is the ground, and it wants to do it. But again, it's all got to do with this created static out there that, is here. So again, back to the issue about total power, is it's important to look at, what are we actually seeing for total power? Let's see if I have any other questions I missed here. What is the soft start technology? We talked about that. And I will, if you send me an email to engineering at AC-DC-HOTLINE.com, and I can send you the link to the guy that actually has that special software. I've done a couple of seminars with him last year. Nice guy to Australia. I've also got, hi, if there is a cheaper, reliable filter for line surges so you can protect the incoming machines. Well, what they're doing is they're taking inductors and capacitors. So it is calculable. I think a lot of these filters are, very expensive. and they do, eliminate a lot of the surges, but it's not always the optimal, point to operate. I'd like to open up to, discussion here. Just unmute yourself and, ask any questions. I'm going to hang around here for another period of time until anybody gets done with their questions. I'm glad to answer if I can. If not, I can, tie you to people that do, understand and know a lot of this. So.
Giving us a lot to think about, Roger.
But I do like my dad always said, let's go to the KISS symbol, keep it simple,
Yeah.
It's really, it's what the problem I see too many technologies is that they're sold, and the people that are given the webinars and the information, they're so entrenched in wanting to sell the products advantages that they don't want to talk about some of the extra pieces that are important on the backside, And
Well, I had good.
Go ahead.
I had a conversation with a couple of engineers that were designing the Pentec and Xylem. What they do, they partnered up with Vfd, and we were talking about this because these are submersible motors in this particular case. And to be honest with you, the Vfd engineers really had no understanding of what these VFDs were doing. And I actually had a VFD expert on the line. It wasn't me, I was part of this conversation. And they literally didn't understand what you're talking about. So some of the filtration that we've been talking about has been really good, but then now I've been made aware of like radio frequency interference, Are you there?
Yeah, I'm still here.
Radio frequency interference, where you have several of these drives in a proximity. That's a whole nother thing that I've never really investigated. So this information is
Well, and all that has happened because all we're building with this technology is we're building radios.
right.
Because we're all these extra harmonics, these third, fifth, seventh, and then some of them get clear out to the 21st, 20. I mean, it keeps attenuating, and it's kind of like what Tesla originally, that's why he understood so much way ahead of his time, because a lot of people think, Marconi created the radio. Actually, Tesla's patents show that he actually did it ahead of him. It's just that, William Power tended to go further. A lot of people think Edison is the inventor of everything in the world, and a lot of times Edison, was just simply, there he had more access to more documents and patents. And I've been to his place in New Jersey, and he just had a bulk of information in the industry. But at the end of the day, a lot of the people that necessarily were the creators of things weren't always the ones that were remembered and known. And so that's why I've studied, so much about Tesla. And, the other thing is I look at the long-term effect of what's going to happen here is we've got, a much more complex controller, and they're sticking these out in the middle of, nowhere in an irrigation site that is, the toughest, harshest environment. Again, keep it simple. Just get those pump curves, get the total GPM back, and it's the optimal way, because it's, again, just going a little bit deeper dive on your original design engineering and or the application, because even the change of lift of water levels are dropping dramatically out here in California. So it's changing where the pump curve is, and we can change and adjust it with the VFD and kind of clear it up, but it's not necessarily the best way to do it. Sometimes you got to bite the bullet and pull the pump out, trim the change the impellers, or, some of them may just be worn. I was talking to a guy up in Minnesota last week, and, he was saying, he was wanting to put a VFD on a pump and da da da. And I said, well, when have you had the pump tested and checked? What has been the last point of that pump efficiency curve? You may have worn out bolts in there. I remember when I was in the Boston, I was working over in at a job site where they're doing a pump that was pumping up to a lake for one of the cities over there. And he was showing me, he said, the type of material they used on the impellers, the water was actually chewing up the impellers for like a year and a half. And so they just kept trying to compensate by taking more speed. Well, then even where they were buying the new impellers was not the pure old impeller. And so the impellers were wearing out, way too fast. So they actually pulled back an old impeller that was like 15 years old and put it back in to cover their problem until they could find out what the actual makeup of the impeller was. Again, back to what we're really trying to do is, controlling this power, properly from the sine waves and, getting it back. And agreed, there's not a lot of education on the full VFDs and technologies. So I think it's important that we bring out what's really happening, because a lot of the schools that are teaching VFDs, well, they're getting their technology to teach the class from the manufacturer's technology. I was very fortunate in my life. I went to a school in the West, and they taught us all the way back to the original fundamentals of that Tesla Bible. And I'm like, I was so grateful to get that information, because I just see things different. I don't take everything on face value of what somebody's trying to sell me. I want to make sure that we're getting things back to efficiency point. It's done me good over my career. I've been in this industry for a long, long time, and I truly love it. I'm so appreciative of my dad. He would never let me use the word can't. He taught me well to keep digging deeper. And, he had an 8th grade education, built 7 motor companies and manufacturing facility. He had an 8th grade education, and he just a determination that I've never seen. That's what's important that we pass on.
Right, I agree.
I'm talking here. Please ask questions. Anyone have anything?
Mr. Fritz, I know this is verboten in the drive manufacturer's literature, but I've seen plenty of times where they've ran the incoming power and the motor conductors over a significant length together. I know that's not good, but can you explain why that's not good?
Well, it's not good because, let me go to the drawing. So originally, because the waveforms were the waveforms were coming in were all sinusoidal between A, B, and C. So we had very low changes in potential. But when we started drawing all these PWM pulses here, again, it's frequency and noise. The power lines coming in actually start coupling those frequencies on you. And so this pulsing that's going on out here, if you go, let's say 1,000 feet away from where you're getting your power source or from your transformer, it actually starts, the signals to each other, because they're radio, they start connecting to each other and will send these, again, high spikes. And so it just kind of, blows up in your face. I mean, all of a sudden you've got, all of this, PWM input power reading all these spikes and each other, and so it's literally just, it's all radio noise. We're back to what he was saying, creating all these noises. So then if they put these, If we put, there we go. Okay, yeah, so this is actually the power quality. You know, again, these are all the various, you know, filters out there that are in the market, and this is turning into a huge business because, you know, again, you're putting all these extra inductors. Well, it's all to eliminate and get rid of those harmonic noises, and it also will even distort the wire. So over a period of time, you know, the old 2/8" wire that we had out there, you're supposed to put in inverter cable wire, and then inverter cable wire on the output, and you're supposed to put in, you know, but a lot of this is now coming out. You know, the VFDs really got a big start in the 80s, and I saw it because actually I was involved with Toshiba back then, and I was trained by, you know, some of the original guys that were building VFDs with hockey pucks, and there was no way you could actually set the drives digitally. You had to all do it with potentiometers and reading little voltages, and the sizes of the VFDs were, you know, 3 to 4 times the size. 5 horsepower drive originally was about the size of a phone booth. So back there was a couple questions. One question was about they make a lot of different types of filters, but it's really important to go back to the meter. You know, what do we have for a problem out there, and then design it to what it is, because every circuit is a little bit different. There's not one special answer for any of it. That's why I highly recommend. I've used this Fluke meter. It used to be a 434. It's one I have, and it didn't have all the extra pumping stuff they did in today, but it is a good meter. There's other ones out there, you know, but again, look at what's going on. Then you create a solution, but also we want to create a long-term solution, so we're not, you know, resetting, you know, 10, 15 years from now, the capacitors are all failing in the drives, and so you got to go rebuy, you know, a very expensive piece of equipment. That's why I'm highly recommend, you know, to go back to the original thought pattern of keep it simple, go back to, you know, the sine waves. You're not creating, you know, this, you know, radio frequencies and noises. That's what I think one of the fellows was mentioning. You know, the actual harmonic frequencies that are created on the power line. You can literally drive down with your AM radio, you can hear them. Especially on the older ones that were, you know, the carrier frequency was much lower, and so you would hear it in the 800 and 600 band, you know, radio stations. And so again, they're trying to band-aid it, you know, with these power quality devices. Any other questions?
Well, Roger, I really appreciate your time and your information. I have to check out now, so thank you so much.
Well, thank you, Frank. I appreciate your feedback. It's, you know, I really learned in life. It's what I was taught young, I need to pass on. So I just like to help. And
I definitely appreciate it. Love learning this stuff.
All right.
Yeah, thank you.
Thanks, everybody. Thanks,
Yeah,
Eric.
thank you, Roger. This was very informative. This is very good.
Oh, I appreciate the feedback.
Thanks so much. Take care.
Thank you, guys.
Bye.